good afternoon, everyone. So welcome to the colloquium today. And today we have a great pleasure to invite Dr. Chia-Yu from MPE. And Dr. Hu actually was he was originally from Taiwan and got a master degree and a bachelor degree at the National Taiwan University. And later he went to Germany for his PhD for MPE. And after then he received his PhD in 2016 from MPE and the short postdoc position at the MPE. Then he got another fellowship from Flatiron Research Institute in New York. And now he returned to Germany being a postdoc fellow at the MPE. And Chia-Yu is a world expert on the supernova simulation, focusing on the feedback and its impact on the galaxy evolution. And he also got a very nice award from Randolph Kippenheim Prize, I think from MPE, for the best student publication in 2016. So now today, Chia-Yu will share his research on this very cutting-edge simulation about the supernova feedback and thus on the galaxy simulation. So I leave the stage to Chia-Yu, please.
Thank you. Let me share my screen. Yeah, okay, thank you for having me. It's a great pleasure to be here, and thanks for participating remotely. Yeah, so today I'm going to talk about some chemistry in the interstellar medium in a context of self-regulated ISM in hydrodynamical simulations. This is the work I've been doing with Amir Sternberg and Evin Van Dishuk and Andreas Schuba. So why do we care about chemistry? The main reason is because observationally we know that star formation occur in molecular gas, in molecular hydrogen gas, H2. So here you see an image of a galaxy. On the left, you see the star formation activities in the red, traced by H alpha. On the right, you see the molecular gas as traced by CO lines. So you see that they are nicely correlated with each other. So we know understanding the molecular hydrogen and its properties tells us a lot about how star formation occurs and how it drives galaxy formation. And here, if you look at the star formation rate as a function of H1 on the left, you see almost no correlation with the atomic hydrogen. On the other hand, if you look at the star formation rate as a function of molecular hydrogen as traced by CO, you see a nice linear correlation. So just a quick recap of the ISM chemistry. The molecular hydrogen is formed mainly on the surface of dust grains. This is the most efficient way to form H2. There's another channel called through the gas phase, but that's much less efficient. So in the ISM typical conditions, most of the molecular hydrogen is formed on dust grains. On the other hand, H2 is destroyed by starlight, by UV radiation in the so-called Lyman-Werner band. So as it's destroyed by the UV radiation, it also shields by itself, both by itself and also by the dust. So on the right, you see an illustration of the structure of the ISM, where you have the radiation coming from the left. And as you accumulate enough column density, you see this H1, H2 transition, where molecular forms at around AV of 0.6, or the visual extension of 0.6. On the other hand, CO, the tracer for molecular hydrogen, forms at a higher surface density or a higher column density. So CO forms mainly in the gas phase, but it also rely on dust in the sense that the formation of CO requires the existence of H2. So here just one of the main channel, and the destruction is similar to the H2 that is being done by the UV radiation. So similar to H2, CO can be shielded by dust, by H2, and also by CO itself. So in this picture, we see this CO formation occur at a much higher column density. So in a spherical structure, we have this classical picture where you have the H2 form at a earlier time, and as you go deeper into the clouds, you see the CO formation in the inner part. However, we know ISM chemistry depends sensitively on the metallicity. The main reason is not actually related to metallicity per se, but it's actually related to dust. Because at lower metallicity, you also have less dust, which means you have less shielding, which means you have less protection. So the molecular clouds are subject to more UV radiation. This means that the CO surface will shrink deeper into the clouds. As you can see on the bottom cartoon picture here, the CO, which is indicated by the pink, shrinks and eventually disappear at low metallicities. In contrast, the H2 boundary it also shrinks, but doesn't do so as fast as CO. And this is mainly because H2 is capable of self-shield. So this is so it doesn't rely on the dust shielding. So at low metallicity, you can see there's a lot of H2, but you don't see much CO. This is the so-called CO dark H2 gas. So because of this reason, H2 emission is notoriously difficult to observe, especially at low metallicity. So at metallicity below around 0.1 solar, you almost never see CO unless you have a very good telescope. So here showing the CO luminosity of a galaxy as a function of metallicities. So below around 0.1 or 0.2 solar metallicity, we only see the limit, so the upper limit. So this makes people believe that there is a large H2 reservoir that is not traced by CO. The question is, how does the ISM chemistry change when we decrease the metallicity? Now, here comes a technical challenge. In order to do so in a numerical simulations, we need to do two things. On the one hand, we need very high resolution, sub-parsec resolution, because we know that the dense gas, so because we know CO only exists in the densest gas at low metallicity. So we really need to resolve this dense structure. But on the other hand, CO network, the chemistry network, is very complicated and it's very expensive to solve. Which means that when you design a simulation, you have to make a compromise between these two factors. So previous simulations either adopted a simple network, which tends to overproduce CO, or they just don't do chemistry altogether and try to push to a higher resolution. But by doing so, they are forced to post-process the chemistry, which means that the chemistry have to be assumed in a steady state or in chemical equilibrium. The second challenge to do so is to resolve gravitational instability. Here is a phase plot, so-called phase plot, which is a temperature, gas temperature as a function of gas density in the ISM. And different dashed line indicate different Jeans lengths. This is each line represent a constant Jeans length. And you can see in order to resolve these each line represent a constant Jeans mass. So in order to resolve the mass scale in a Lagrangian code, the resolution we require is extremely high. For example, in the large cosmological volume simulations, the resolution is only such that you barely resolve the warm gas, while in the zoom-in type simulations, such as FIRE, you're resolving the warm gas perfectly, but the cold gas you cannot get the cold gas. So that's why we go to such high resolution around solar mass scale, is because we really want to capture the formation of this dense gas and its gravitational collapse. And the final thing we have to worry about is to resolve feedback, to resolve individual supernova explosions. This is a long-standing problem in cosmological simulations where they cannot afford high resolution. But what tends to happen is that when you don't have that resolution and you try to dump the thermal energy into the unresolved medium, what happens is it won't do anything. So here's an example from left to right. You see from high to low resolutions with the same supernova energy. You can see at high resolutions, you see this nice blast wave developing, while at low resolution, it doesn't really do much. And also, you don't get the hot gas, which will eventually escape the galaxy as the galactic wind. So this all points to the fact that we need very high resolution. So what we try to do in this work is to focus on a patch of a galaxy, as I shown here. So on the right, you see our simulation box, which is a kiloparsec on the side, and it's elongated to 10 kiloparsec on the vertical direction. And the model is similar to the solar neighborhood. And we run 4 different simulations with metallicity from 3 solar to 0.1 solar. And each simulation is run for 600 million years. Okay, so a little bit about our simulations. We use the Gizmo code, which is a Lagrangian code, and each particle has 1 solar mass, which roughly corresponds to 0.1 parsec at the density where we can still resolve the Jeans mass. And we also include a time-dependent H2 chemistry. And for chemistry, another thing we need to consider is how we do radiative shielding. And our shielding method is based on the Hilpik's algorithm, where we define different sightlines and calculate the average sightline for each cell up to a predefined radius of 100 parsec. And we also include star formation and the feedback from supernova and photoionization. So on the right, you see a face-on snapshot of the H+, H1, the atomic hydrogen, and H2 on the left, on the right, sorry. So these are all calculated directly from the simulations. But so far, we do not have CO yet, because as I just said, CO is very expensive, and we cannot afford to run the full network. So our solution then is to do post-processing using a much more accurate chemistry network. But the crucial difference with previous work is that we're using the non-equilibrium H2 abundance as an input while evolving everything else to equilibrium, to a steady state. This is a crucial difference because we know H2 formation is very inefficient and the non-equilibrium effect is very significant, as we'll see. So you see that by post-processing, we can get C plus the atomic carbon and CO. So one interesting result we see is that we see a correlation between the gas density and the column density for shielding. And this is an illustration of how that column density is defined. As I just said, this is based on a Hill-Pick method. So for each gas cell, we first define a sphere of 100 parsec, and then we have 12 different sight lines, and we accumulate the column density for each sight line, then do an average over these 12 sight lines. So each gas cell can actually have a column density for shielding. And if we see that column density as a function of gas density, as I shown here, you see there's a very nice correlation, and which is actually insensitive to metallicity. And the reason for this is because what actually decides the column density is the Jeans length. So if you calculate the gravitational, the thermal Jeans length and multiply by the gas density, we actually recover the column density it sees pretty well as a comparison here, except in a warm gas where gravity is not important. This means that for a given density, we can actually estimate the typical cloud size based on the thermal Jeans length. But so far, I've been talking about just a geometric average over the sight lines. But what actually matters for shielding is the so-called effective column density, where you calculate the average of the shielding function for dust. So dust shielding goes like exponential as an exponential function. So if we do an average in this way, then we see a slightly different correlation at different metallicities. But this is not a geometric effect, because as we just saw here, the geometry at different metallicities is actually very similar. What actually causing the difference here is it's basically just the different dust extinction in the AV. But the most important point is that the column density is actually an increasing function of density. Here, now we're looking at the transition between H1 and H2. Here I'm showing you the H2 abundance as a function of gas density on the left and the column density on the right. As we just saw, that because there's the correlation between the two, these two plots looks very different. Sorry, these two plots looks very similar to each other. But here I'm comparing two different models, where the solid case is the time-dependent model, our fiducial model, while the steady state case is a model where we run everything, including H2, up to a steady state. So the difference between the two tells you how much H2 is out of equilibrium. So you see, overall H2 is always underabundant compared to its equilibrium abundance. And the reason for this is because H2 formation timescale is very long. For example, at solar metallicity and at a density of 100, the formation timescale is about 10 million years, which is actually comparable or even lower longer than the typical dynamical time in the ISM. And this timescale increased linearly decrease linearly with metallicities. So you can imagine at 0.1 solar metallicities, the formation is very inefficient, so it never has the chance to reach the equilibrium abundance. Now, if we substitute a dynamical time that scales like 3 million years, and with a simple Paul law here, we can actually reproduce analytically this H2 profile as a function of density very well. On the other hand, if we now look at CEO, which is the middle panel here, we see a very different behavior. So first of all, time-dependent and steady-state models are very similar, which tells us that CEO is pretty much in steady state. And secondly, it is not affected by the difference in the H2, which is not clear a priori because CO formation relies on the shielding from H2. The reason it doesn't affect it so much is because CO forms at much higher densities compared to H2, such that by the time where CO start to form, the accumulative column density is already very high. So which is why it doesn't affect CO. So it turns out since we can calculate shielding with just by the density, we can turn this into a completely local problem, and we can use a simple 1D model to nicely reproduce the very time-consuming hydrodynamical simulations, as I'm showing here. So you can see that the solid line and the dotted line, dashed dotted lines, they are in perfect agreement with each other. So the bottom line is that the time-dependent effect or the dynamical effect strongly suppress H2 formation, but not so for a CO formation. So if you see the total abundance of H2, you see a very big difference between the two models. While if you look at CO, you see very little difference. And the implication is that you don't have the CO dark H2 fraction will be overestimated if you assume a steady state chemistry. Now, so far we've been discussing just the chemistry, but we haven't considered the radiative transfer effect that ultimately leads to the observation. So we use the ROD-MC code to do the radiative transfer to calculate the CO line, CO120 line from the simulation. So on the right panel here, you see an example of the CO line emission. And we want to quantify is this factor, the so-called axial factor, is the conversion factor of CO to H2, where if you observe certain value of CO intensity, you can infer the underlying H2 mass. So if we look at the kiloparsec integrated average XCO as a function of metallicities, we do see a trend that it is a decreasing function of metallicities. So this is already expected. But comparing to, for example, here different lines represent different observational constraints from the literature, while our fiducial model, the time-dependent model, is the solid red dots. You see that we're systematically lower than the observational constraints. However, if we compare our steady-state model with observations, we see actually agrees much better, and we know the reason for this. This is due to the fact that we just discussed. This is because the H2 is underabundant, is in fact not in steady state. So if you try to estimate XEO using the so-called either by using cloudy modeling, assuming a steady state chemistry, or if you assume the star formation only occurred in H2, so kind of using the Kennecott-Schmidt relation to inversely infer XEO, you will also overestimate XEO by a similar effect. And here is a map of XEO. So you can see that at parsec scale, the XEO actually varies significantly. So you see orders of magnitude difference in this map. And in the diffuse gas, you see this is the orange regions here. You see very high XEO, which is volume filling. While in the purple regions, you see a low XEO corresponds to the dense gas. And this purple area actually is close to the Milky Way value. So if we look at the distribution of XEO, you can see it's very different. It depends on how you weight the histogram. If you look at the histogram of XEO in an area weighted way, meaning that each pixel is equal, then you see most of the area is filled by the diffuse gas with very high XEO. On the other hand, if you weight it by the CO intensity, you see that it's then peaked at a much lower values. So this tells you that most of the CO emissions coming from the dense gas where the XCO is low. And here is the CO intensity as a function of H2 column density. And because of this definition of XCO, we can also plot a constant line. For example, here I'm showing 3 different lines corresponding to 0.1 XCO. So the XCO Milky Way is a solid line, and here is the 10 times lower and higher lines. And you can see that the variation mostly occurs because of the CO formation. So at this column density of around 10 to the 21, this is where CO starts to form. And once it starts to form, it kind of saturates to this Milky Way value. While if you look at low column density gas, you're looking at diffuse gas with much higher XCO. And if you look at the XCO as a function of the H2 column density times the metallicity here, and you see XCO is initially very high, and as you reach to a certain value, you start to drop and approach the Milky Way value. And this value, this transition point, roughly corresponds to this 3 times 10 to the 21 centimeter square, which roughly corresponds to AV of 3, which is where we expect CO formation to occur. Which is why we expect dust shielding to be efficient. So this tells us that the dust shielding is a controlling factor for XCO. So, but observationally, we usually have different telescope beam size, and we try to investigate what we'll see at different beam sizes. So here we're downgrading our 2 parsec pixel size systematically towards high beam sizes to see what happens. Now, if we plot XCO is a function of CO intensity, as I'm showing here. And you see different lines here representing different bin sizes. You can see the relationship between XCO and CO intensity actually changes with the bin size. And this is the effect is due to an average because the large scale XCO depends on the sub-bin distribution of the gas. And if you look at the XCO at a particular bin size, it turns out that the average can be written as a intensity weighted average of small scale XCO. So this tells you that the large scale XCO will be systematically biased towards the dense gas where you have the highest CO intensities. And as you do the averaging, you're driving the relationship downwards because of the averaging. So in the interest of time, let me skip this one. So in the last part of the talk, I want to tell you about something related to the interstellar dust. So we know that dust is very important for the interstellar chemistry. We just saw its effect on shielding and its effect on CO formation. We also know that dust is actually not spatially uniform in the ISM. For example, if we look at the LMC and the SMC, the gas to dust ratio as a function of gas surface density, actually you see a decreasing trend, which tells you that at higher gas surface density, you expect higher dust abundance or higher dust to gas ratio. So we try to model this effect, and the way the reason for this is because there's low in the ISM, dust is constantly being produced and then destroyed by different processes. Otherwise, you will just expect uniform dust to gas ratio because of the turbulence and the mixing. So we include a dust evolution model, which is where the destruction by supernova shocks is based on the model we developed a few years ago that considered both the thermal and non-thermal sputtering and tracking the dynamic of dust through different processes such as collisions and plasma drag and the so-called betatron acceleration. And the production from AGB star, we just take the dust yield from the literature. But the most important process in this context is the so-called dust growth in the dense gas. This is a process which is very similar to H2 formation on dust grains. But here, instead of a hydrogen atom, here you have a metal. For example, either carbon or a silicon collide with the dust grains and stick onto the dust grains and eventually grow the dust by this mechanism. And the growth timescale is the following. It depends on the density and the temperature of the gas because of the collision, and it depends on the gas phase metallicities because of you need the ingredient. It also depends on the grain size because smaller grains provides larger total surface density, total surface area. And there's a sticking coefficient at the end, which is still quite uncertain, but we model it just as a simple step function, which means above certain temperature, is turning off completely. So the formation timescale at 0.1 solar metallicity and at density of 10 to the 3 per cubic centimeter, is actually quite long. It's around like 10 million years, which is actually quite comparable with the H2 formation timescale. Here I want to show you a movie of this simulation. So this is not a patch. This is a isolated dwarf galaxy, similar to the nearby dwarf galaxy WM. Here I'm showing you from left to right. We have total gas surface density, H2 and H1. And on the bottom, we show you the temperature of the gas and the dust to gas ratio and the UV radiation field. So one thing I want to highlight is the fact that the dust to gas ratio is not a constant in the simulation, as I just described, because we have constantly creation and destruction in the ISM. And then you can also see the effect of turbulent mixing, where these small clumps of high dust abundance gas quickly homogenized by turbulent mixing. So here I want to show you the chemical abundance of different species. This is in a model without dust evolution. So on the top, you see the H2 abundance as a function of density and column density. You see, first of all, the transition is at a very high density at above 10 to the 5. This is because the H2 formation timescale at this particular metallicity is so long that you never reach the equilibrium abundance. If we compare to a model with the dust evolution, you can see a difference in H2 abundance is very low. So you see very little difference in the H2 abundance if I go back and forth between the two models. And also the green is the dust to gas ratio relative to solar. You see that the reason it doesn't make much difference for H2 is twofold. The first of all, the H2 can self-shield against UV radiation. So in that case, it doesn't really care about dust shielding if it can shield the radiation by itself. But secondly, it's because dust growth is also very inefficient. So you only see a high dust to gas ratio at the densest gas where the dust abundance is already high anyway. So it doesn't help the H2 formation. In contrast, if you look at CO formation, the transition of C plus C and CO, you see without the dust evolution, you don't see any CO. It's just C plus all the way. While if you include dust growth, you increase the dust to gas ratio at the highest densities, such that you provide enough shielding for CO formation. So if you look at global properties of the galaxy, on the top, this is the total H2 mass. We see, as we just seen, we see very little difference between the model with and without dust evolution. But if we look at CO, we see orders of magnitude differences between the two models because of radiation shielding. The total star formation rate is also very insensitive to the dust evolution model, because as we just saw, the dust growth only occurs at the densest gas, and what determines the total star formation rate in the galaxy is a not so dense gas, maybe around a density of 100 or so. So it doesn't care whether you have much more gas at 10 to the 5 or not. So the final point is the spatial variation of dust abundance. So we see that the dust to gas ratio can vary with gas surface density observationally. So this is also seen in our simulations. On the right here, I'm showing the same plot dust to gas ratio as a function of gas surface density, and the 3-parsec is our pixel size, the finest pixel size. You see, it is indeed an increasing function. But another interesting point is we try to see the effect of beam size, because as we just saw, for XCO, there's a very strong effect for the telescope beam size. If we try to do the same, try to systematically degrade the telescope beam size, we don't see any change in this relationship. We just see that the highest gas surface densities get diluted away, but the relationship almost stays constant. And the reason for this is because the mixing is very efficient. So you also see that in the movie because of feedback and turbulence in the ISM. Whenever you have any inhomogeneity in the dust to gas ratio, it quickly gets mixed with the rest of the ISM. This is why we don't see a dependency on the beam size. Okay, so here's my summary. So I presented the high resolution simulations coupling with chemistry and dust to investigate from first principles the star forming gas and the chemistry tracers. So we see that the time dependent effect strongly suppresses the formation of H2, but not so for CO. And we see a correlation between column density and volume density, where you can turn the non-local problem of chemistry into a nicely behaved 1D problem that can be solved very quickly. We also see that at small scales, XCO has orders of magnitude variations in the ISM, while at large scale, it's controlled by the gas distribution within the beam size. So XCO actually depends on multiple factors, not just metallicity. And we've seen dust growth is a very significant process to facilitate the CO formation up to the observed value, but it has very little effect on on H2 formation. And finally, the dust to gas ratio has a positive correlation with the gas surface density, and it has very little beam size dependency. Thank you.
Thank you very much. Chia-Yu, is a very nice talk. And now time for open for questions. Please use the raise hand function. Any question? Which one? I didn't see any. Oh, who? Then I have a question.
Sure.
So Chia-Yu, I was wondering for this for your high resolution hydro simulation plus chemistries, how does the resolution affect, or can the simulation converge?
Right.
You increase the resolution, and how the chemistry, physics, I mean, can converge like
Right.
hydro. As you know, like a MHT simulation, usually they can not be converged because due to this resolution effect. So
Right.
I
So
was
we did.
wondering how sensitive about this part.
Right. Yeah, that's a good question. So actually did convergence studies.
Mm,
We think that we're converging actually quite nicely.
mm,
So here I'm showing you our convergence studies.
Mm.
The key to convergence in chemistry is actually the density distribution, the density PDF. Because if you're missing, because chemistry occurs only in the dense gas,
mm,
so if your simulation is missing the high density tail, then you are not going to be converged. So
mm,
here I have different resolutions from 1 solar to 100 solar masses per particle. And you see, so at the lowest resolution, you don't have these high density tails, right?
mm,
But as your resolution increases, you start to have convergence of these high density tails. And if you look at for example, the total star formation rate, it converge. So star formation rate is actually the easiest to converge, but the chemistry is more difficult. For example, H2, we see convergence roughly maybe occur at around 3 solar mass resolution. CO is a little bit difficult because it differs at different metallicities. But CO is reasonably converged, but not perfectly. So we're maybe seeing a like 30% difference between the highest and second highest resolution. Yeah, so there is a convergence um, concern, and we think we're very confident for our H2, but CO we think we're at least on the verge of convergence.
Okay, thank you. Ding-Yuan, you have a question?
I think Ida has a question first.
Okay, Ida, please.
Hi, Chia-Yu. Thanks for your talk. I have
Thanks.
several questions.
Good.
Yeah, let me start with the first one. So, I wonder when you calculate the slope, the variation of dust to gas ratio with the gas surface density,
Right.
does the scaling relation change when at different metallicities? Yeah.
Wow. So the question is I don't know, because for this particular simulation, I only have one metallicity.
Yeah.
This is try to model a particular dwarf galaxy where so in this sense I cannot say much.
Okay,
but in principle you can see that that play a role, right? Because metallicity, because the growth timescale is explicitly dependent on metallicity. So in this sense, I do expect a metallicity effect.
Yeah. Because I think this is I don't really often see simulations comparing dust to gas ratio to gas surface density with constant metallicity, like the plot you show, like the observations you show from Romain Duval's studies.
Right.
I was guessing because they have 2 dwarf galaxies. So I was just guessing if you just try to reproduce 2 different metallicities to simulate the 2 galaxies they have.
Right. So this is not a SMC or LMC galaxy. So this is in fact much smaller. 5 times less massive than SMC. So we cannot make like the fairest comparison, but we can see a similar trend for that. Yeah.
And is this effect better traced by gas surface density or 3-dimensional density?
So theoretically, it it should be tracing the volume density, the three-dimensional density better, because that's the fundamental dependence.
Yeah.
But this is what observation. This is just try to to plot it, to plot what observers would see.
And do you happen to have simulated some spiral galaxies?
No, the answer
No, okay.
is no, because we cannot afford that.
Okay.
So, if you try to do high resolution simulations, you only have two options. You either simulate a dwarf galaxy, as we did here, or you just simulate a patch of a galaxy, which is another thing I showed. So we still cannot simulate a Milky Way type galaxy down to the resolution we can resolve the ISM. That's still not feasible.
Okay, got it. Thanks.
Okay. Big one, please.
Thank you for your talk. So at the beginning of your presentation, you mentioned that the CO abundance depends on the metallicity, which is due to the dust shielding. I'm just curious because in principle, lower metallicity also means lower carbon and oxygen, right? So so I just wonder which effect dominates. Or there's in fact a degeneracy between the abundance of the metals to form CO as well as the dust shielding.
Right. So that's a good point. So that's the first order dependence, right? So as you at low metallicity, you also have less ingredient to make CO. That's for sure. But on the other hand, you also have less dust, because the dust, because the H2 formation depends on dust linearly. So they both scale linearly. That's what I'm trying to say. The H2 abundance and the CO abundance, if you just think about the material they need to form, they both scale linearly. And so in this sense, you expect them to, you expect the ratio to stay the same, right? You expect a XCO factor to be constant across metallicities. But I think what's really causing the systematically what is really causing the metallicity dependence of XCO is really dust shielding, because that's adding another effect on top of the metallicity effect.
Okay.
Does that make sense?
Shen-Yuan, please. Shen-Yuan and
yes, thank you very much for this very nice talk. I have a very naive question. The question is about metallicity, or the definition of metallicity. This is the metallicity at the very initial, sort of the input metallicity at the beginning of the simulation. Is that correct? Because I imagine metallicity itself will evolve as your system evolves, right? So how? What's
that's actually incorrect, because in my simulation, I do not have a metal enrichment, which means that the gas phase metallicity stays the same all the time.
So the stellar sort of feedback to the metallicity is not considered in these simulations, or you don't enrich your
stellar feedback. So stellar feedback is included, but it has no dependency on. It doesn't depend on metallicity. Did that make sense?
I would.
So we know that supernova is the main driver for regulating the star formation in the ISM, and supernova feedback particularly is insensitive to metallicity, because cooling is so fast that it doesn't care about whether you're 0.1 or solar metallicity. So that's the justification for using a constant metallicity. Does that make sense?
Well, I need to think about it. Yeah, thanks.
Yeah, sure.
Papa, please.
Jerry, thanks very much for the nice talk. So I have a practical question. So if we have a galaxy that we already constrain the oxygen abundance by stellar spectroscopy, then do you think dust is a better tracer for total gas mass, or CO would be the better tracer for total gas mass?
Yeah, you're asking a very difficult question. So I don't have a good answer for because we know that these are two different. These are like alternative tracers for H2, right? I would say that they both have different systematics. Obviously, for XCO, we see there's a lot of spatial variations, and it's not just a metallicity effect. But for dust, if we're relying on dust thermal emission, then we also have this systematic uncertainty about the assumed dust-to-gas ratio, isn't it? So it's always a little bit circular when you try to use dust to derive the H2 mass, because you have to so you measure the dust emission, and you measure the H1, and you try to calculate the total gas. But for that, you have to know the dust-to-gas ratio. And I guess what people tend to do is to use metallicity function. But I think it's still not so certain that I would say dust is definitely an alternative, a better tracer for H2. I would just say at metallicity where you don't detect CO, then you have to rely on dust.
So in your simulation, the dust to gas mass ratio is not so well correlated with the metallicity.
Right. It's actually only have so in the model. So in my simulation with dust model, I only have one metallicity.
I see. So dust evolved too much, so it doesn't give you a usable constant gas to dust mass ratio for the bulk of gas in the galaxy.
Dust actually so. No, if you dust, if you only have like if the dust growth only occur in the densest gas, then it probably doesn't affect the global dust to gas ratio. Right. So in that sense, it's probably okay. So I can see if you have observationally, if you have a resolved observation where you can see a sight line where you are confident there's no H2, so you can sort of estimate the dust to gas ratio for that sight line, for diffuse sight line. Then the question is how. So is it fair to assume that the dust to gas ratio is still the same when you apply that to the sight lines with CO, right? So I guess that's the problem.
Yes, I see.
So no, so my simulation cannot answer this big question.
I see. Thank you.
Not yet. Thanks.
Thank you. Okay, Ida, the final question.
Okay, thanks. I want to following up Shengyuan's previous question. So
right.
I just want to make sure I understand correctly. Did you say you in the simulation you set the gas phase metallicity as a constant?
That's correct.
Okay, and so what's the rough number of your dust to gas ratio and metallicity? Like both 10 to the negative 3.
In which simulation? In the box or in the galaxy? Because I've showed two.
In the galaxy.
So in the galaxy, So the gas phase metallicity is 0.1 solar, and the dust to gas ratio is 1% solar, and that's motivated by the observational trend that you have the broken power law at low metallicity.
1% solar. So that's like something like 10 to the negative 4. 10 to the negative 4.
Yeah,
That's
10 to the minus 4.
10 to the minus 4. Okay.
Roughly.
Yeah. Okay. Yeah. I was just want to make sure if we have some, because I think I saw dust to gas ratio like 10 to the negative 2 or 10 to the negative 3 in some of the slides.
I see. That's because I normalized to solar.
Oh.
Yeah.
Okay.
Sorry. Yeah. So it starts with 1% solar, and which converts to 10 to the minus 4 in the absolute value. So I guess I show the absolute value. So if you see 10 to the minus 3, that's the absolute dust to gas ratio.
Okay. Got it. But if it's 10 to the minus 3, and
Right.
if it's 10 to the minus 3 and with 0.1 solar metallicity, does that mean almost all the metals goes into dust?
No, that means almost all metals is in the gas phase, isn't it? Because
Dust to gas ratio 10 to the negative 3, and 0.1 solar means metallicity is also 10 to the negative 3,
yeah,
right?
I see your point. Yes. So
Yeah.
at the highest gas, at the highest gas densities, yeah. So most of the metals is in dust. It's locked in dust at the highest densities. I guess that's what you meant.
So what you actually fix is total metallicity, not gas phase metallicity, right?
That's correct. That's correct.
Okay.
So so that's sorry. So that's the correct statement.
Okay, thanks.
Okay, thank you. Time's up.
Thanks everyone.
Thanks Chia-Yu for a very nice talk, and thanks everyone for joining. Have a good afternoon. Bye bye.
Thank you. Bye.
Bye bye. Thank you.